University will talk us about also online learning with adaptive algorithm, more specifically on BOA with algorithm online.
Yeah. Okay. Thank you, Yanning, and the organizer for inviting me here. So it's a pleasure to present you an online aggregation algorithm called BOA and a specific setting. So my talk will be a bit more theoretical and a bit more specific than the first one. Yeah, so that's why we switch the order of the talks. So my aim in this work was to understand why aggregation could lead to a nice estimation of quantiles. And in my opinion, the formalism used by Pierre was not really the good one to tackle the problem of quantile prediction, because quantile is related to some distribution. And so we really need to find another setting, and a setting where we introduce in some way a stochastic environment. So the setting I will use is the online learning setting with stochastic environment that comes from Sebastian Jerchenevich in his PhD thesis in a general way. So we assume that we observe a couple YT, XT recursively, so online. And this process YT, XT is stochastic, but we do not assume anything about the distribution. All right. So then the aim of the online learning is the following one. We have the variable of interest, YT, and we want to predict YT plus 1, given in advance XT plus 1, the explanatory variables. Then they can come from the past, or they can be, so they can include the past of the YTs, or they can be completely different than YT themselves. And so for that, we need to find and to produce a predictor, f hat t, which I call a learner, that is a function that from explanatory variable will try to produce YT. And this function must depend only on the past observations. So on the couple YS-XS up to time t. All right? So here, it's natural to embed this setting into a kind of martingale theoretical framework where we need some information. So the information is theoretically noted by capital FT, and this capital FT is a filtration, so it's the set of events that grows with our observation and corresponding to our observation at time t. And so what is really interesting in that setting is that actually, usually the regret setting or the adversarial setting is set as the most general setting you can use, because you face any deterministic sequence. But actually it's wrong. This setting is even more general, because you can always think of an adversarial nature which picked exactly the process XTYT as being a sequence, so something completely deterministic, so something completely degenerate in terms of stochastic setting, which play adversarially to what you predict. All right? So, in some sense, we are more general than the adversarial setting, and we introduce any kind of stochastic underlying framework. And so we could think of the adversarial setting as if the nature shows the stochastic or the distribution as the worst possible distribution that we can face. And now, in this setting, the prediction of quantile make sense, and we will see how later. First, we have now to think ourselves of what are the experts in this setting. So the experts are now sequences of adaptive learners, in the sense that these experts can be thought as inputs, outputs of black boxes that are statistical and online algorithms. So the important thing here is that we only deal with sequential algorithm in that setting. So we cannot aggregate algorithms that do not respect the filtration. So that's the restriction. And we have to think about the experts as, or candidates of experts as statistical algorithms that are sequential. And then now the aggregation, to shorten a little bit, I write it as an expectation here, because the sum of the weights are equal to 1. So the aggregation, the aim is to find the best possible aggregation of these learners. And so again, these learners are themselves statistical sequential algorithms. And so the only assumption is that they are adapted to the filtration of the information. So, of course, in our construction, it's also very important that the weights has to be adapted to this information, in the sense that in order to avoid overfitting, we need to weight this experts with information from the past only. Okay. And we will see that in that setting, it's very important to keep some and to define rigorous robustness and adaptive definition, so that an algorithm must fit into this and achieve this robustness and adaptivity. And a solution, a reasonable one, is a version of an aggregation. And we will see that the usual one, exponential weight algorithm that was introduced by Pierre, does not fit into this, or does not achieve this nice adaptivity and robustness. Okay. So again, I recall what said Pierre before. So the regret usually is the following thing, is that you look at the cumulative loss of your aggregation, and then you compete with the best possible experts. All right. As a remark, the regret is not necessarily positive, and Pierre shows that you have nice theoretical guarantees for that regret in the adversarial setting. Okay, so now, if you recall what Pierre said, he said, I have a bound which is on square root of log k divided by t. And that's a bound that is called a slow rate bound, in the sense that you have a 1 over square root of t, or let's say square root of t on the regret as a rate of convergence. This rate of convergence are not optimal in many cases, in the sense that you would like to speed up a little bit to be more precise. By using what? You have to assume some regularity on the losses to speed up this rate of convergence. Because if you have only convex losses, that's the best that you can So the usual the usual condition on the losses that allow to speed up is the X concavity. And the X concavity of the loss is defined like this one. So it's a kind of strong convexity assumption on the losses. So it means that you behave a bit like a square loss. Okay. And in that case, if your loss,
So L prime is a derivative.
yeah, is a derivative with respect to the second one. We just look at the loss with respect to the second. Yes, and so if actually the losses are X concave, then it's shown that the exponential weight algorithm of Pierre it works very nicely, in the sense that if you design your weights so that they are exponential minus eta, so eta is the learning weight, and so the loss impure by the expert, then Wolf proves that you have a regret in log m, so it's a constant regret, in the sense that the cumulative losses are bounded through time. Okay, so that's actually a bit more difficult to prove than the proof of the regret of Pierre, because you boost, in some sense, in that case, in that optimistic case for the loss, you boost the guarantees in EWA. That's nice, but of course, as I told you, I am interested in predicting quantiles and potentially high quantiles, and the high quantiles are not X concave, they are just convex. Okay, so they are the losses where actually this guarantees from Wolf does not apply at all. Okay, because well, here how to convince, so you are piecewise linear as a function of y, and so you cannot be strongly convex. Okay. However, if now you think about the use of the quantile loss, you use the quantile loss because the quantile loss satisfies this. So if you look at the conditional expectation of the quantile loss given the past, then if you minimize in the second the quantile loss on the second variable, then you obtain, of course, a conditional quantile. So you obtain, given your past information, the quantile of the distribution of y given your past, because I assume that I'm in a stochastic environment, of the quantile of order tau. So tau again is here the slope is driven the slope here on of the quantile loss, and so if tau is equal to 1/2, I go back to the classical absolute loss in this case, and of course we know that we predict the median in this case. And now, so if you look at this criterion, so the conditional quantile loss, okay, then this criterion, so that's just a small simulation, this criterion is nicely convex and strongly convex. Okay, so you can see that the curve here is much more regularized than the absolute loss. So, in some sense, what we have right now in the stochastic setting, we have that we understand why we use the quantile. It's because actually at each step, if you minimize this objective, you obtain a conditional quantile. And second, we gain some regularity on the curve. So potentially, maybe we can have a better rate of convergence, or let's say a regret bound for our strategy. Okay, an important point is that, so, okay, in VOC, here, so the loss is given, and so basically if you know that the loss is a square loss, you know that on some compact set it's x concave, and you know the constant delta here because you got the loss. So here the learning rate really depends on delta, so on Bob's work, and so in order to you really need to adapt the learning rate to the loss. So actually, if you choose the loss, then you know delta, and that's fine. Here, the problem in the stochastic setting is that now we are using a conditional expectation, and actually the curvature of this conditional expectation, which is nicer, is completely unknown because it depends on a conditional distribution. So basically, you really need to have adaptive strategies in order to have a good learning rate that will adapt to the curvature of this new objective. Okay. So now think of the objective in the regret bound. Then hopefully, if you choose, you recognize the best expert, then you hope that for the quantiloss, you will get close to 0 when you look at the minimum of your expert. But what does it mean if you want, let's say, okay, after one round, at one step, what does it mean if you minimize this loss? Actually, it's clear that it means that x is equal to y. So it means that you will choose in your aggregation, or at least at the beginning, you will vote in favor of experts that predict the mean. Okay, and then you depart from the mean in your strategy built on regret, just because you have the average effect in the regret that makes you getting closer and closer to something in distribution. Okay, so it's time to define our objective rigorously. So our objective will be the predictive risk. So that's the conditional expectation of the quantiloss, or of any loss. And what we gain from using this setting, so the stochastic setting, but completely general, and this objective is that the optimum is actually what we are aiming to predict, and also the objective function may be much more regular than the loss, than the quantiloss itself. Okay. So then the next step is to define, as we have done for the regret, a new kind of regret, which is just the cumulative predictive risks minus the best predictive risk for any expert. And a remark is that so again, in the adversarial case, of course, the nature will play the worst distribution, so it can play a deterministic distribution, and we are back to the usual adversarial setting, because we can always consider this conditional expectation as Dirac masses, and so the nature play against you. But also, we can also try to be a bit optimistic, and maybe we are in the ID setting. In the ID setting, what you can do is that you can average, because actually this conditional loss become, so this predictive risk become actually the usual risk, which is fixed. And then because f at t is a learner, so it depends only on the past, you obtain a classical, oracle inequality in the sense that you look at the risk of your estimator, and then you subtract the minimum of the risk of your expert. And so if we obtain a nice bound on this quantity, then we get a nice bound on the usual oracle. So we obtain in the ID setting an oracle inequality on the average aggregation. So that's what we call oracle bounds in the ID setting. Okay, so let's go to quantitative bounds. So again, EWA obtain a nice bound on the regret when the loss is X concave. But in Cesar Bianchi and Lugosi, they discuss the assumption of X concavity, and actually it's a necessary assumption in the sense that if the quantile loss is not X concave, does not exist any aggregation procedure with regret better than the square root of t. So better than the bound that showed you Pierre before. So you cannot speed up the aggregation procedure. So, of course, the idea is then if now you take the expectation of this regret, then the expectation of this regret is also the expectation of the cumulative risk, and you obtain a bound on the expectation of the cumulative risk. So in expectation, EWA works well. But Olivier in 2007 shows that EWA does not work with high probability, and that's in a stochastic environment. What should be seen as, or what should be the definition of robustness, is that in a stochastic environment, you need that such a bound, so such a rate of conversion, or such a bound on the predictive risk should hold with high probability. Because think of a sequence, an ID sequence center. Then in expectation is always 0 when you take the cumulative sum. But of course, the random walk is completely divergent. So it's clear that an assumption like this one only in expectation does not give you any detail about the deviation of your cumulative risk. All right, so what he showed that for any learning rate, and in the most simple case, in the ID setting, so we are not talking about adversarial setting, so the nature just play ID, so nicely, EWA simply satisfies the following, is that the cumulative risk is smaller than a constant times square root of t times certain constant with high probability. So in the sense that we cannot improve, we cannot boost EWA. So it's not robust in the stochastic setting in the sense that in expectation it does well, but maybe not in with high probability. And so the natural question, open question from Olivier was, can we modify EWA so that we get a robust and adaptive procedure in the stochastic setting? So the idea is to build an algorithm that satisfies this, so a bound on the cumulative risk that is a fast rate bound on the cumulative risk and with high probability. And of course, the algorithm may not depend on the convex constant of the predictive risk because it's unknown. It depends on a conditional distribution that may vary through time. Okay, and so as I told you already, this stochastic setting, which is very general, is nicely embedded in the martingale setting because you have already the notion of filtration and information up to time t. So it's quite natural to use the filtration and the martingale. And actually, the differences between the regret and the cumulative risk, it's not hard to see that they constitute a martingale. And so the proof of Pierre was based on Hutting inequality. So it's a concentration inequality, but you can use other concentration inequalities for martingales. And in particular, you have one that is really simple, is just that if you have a martingale and then you are bounded from below, that's a very strong assumption. So all the difference, so delta t, I forgot to tell you, delta of mt is just mt minus 1. That's the difference of martingale. So the jumps are not, of the martingales are lower bounded. Then you denote the quadratic variation, so that's the sum of the square of the difference of martingale. And you have this bound, is that with high probability, the martingale is controlled by its own quadratic variation. Okay? So, applied to martingale, it means that when we go from a regret to the stochastic environment, we obtain that we control the move from the regret to the cumulative risk by a quadratic variation that is observable. So it's just the sum of the square of the losses of the aggregation minus the losses of one expert. Okay, so that's this here. So now,
sorry, I didn't get. Or you go from the theorem to the next. So the theorem gives you a high probability bound, and then what's the point with the new version?
This one?
Yes.
So it's just to recognize the quadratic variation in that case
okay.
for this specific martingale. So it means that you control. So you control the martingale. So the let's say what I call adversarial to stochastic conversion. If you want to move from a regret to a cumulative risk, you control that by a quadratic variation that is like this one. And so actually you can show that this quadratic variation is not controlled more than square root of t in the case of EWA. So that's a very strange quadratic variation term, because it's a term that just depends on the algorithm. It's how the algorithm competes with respect to itself. Okay, so how it fluctuates in the past. So now when you have something like that, and actually I just see, so I forgot here to tell you that you have, so you need here to add the weights outside, the weights that play EWA or any algorithm outside. So you have the sum over J of P GT outside, so you have really kind of variance. And sorry for that typo. So you cannot bound EW, you cannot bound this for EWA, and actually that's this quadratic variation term that is responsible of the gap between a nice regret bound, even in the X concave case, to the bad one in the stochastic environment. So, but when this is observable, then a natural way to deal with that is to penalize. In the sense that, so I know that if this is big, I will not be able to do the conversion. So now I will penalize and add a second order term in the EWA. And that's what I call Bernstein online aggregation, because it comes from this quadratic variation. So it's EWA where actually I penalize the algorithm when itself it fluctuates too much. So in the direction where it fluctuates too much. And then, if the losses are X concave, then the regret of BOA in the deterministic environment pass nicely in the stochastic environment, thanks to this new adversarial to stochastic conversion, because now the algorithm is built to control this term. Okay.
So what do you mean by recursively?
It means that here you have PJT and here PJT minus 1. So, well, yeah, of course, then of course the PJT is just the exponential of the sum of these guys. Okay. So, but I didn't solve my problem. I solved. So, at that point, I understand why EWA is not robust for in the stochastic environment. It's because actually the weights fluctuate too much. So even in the ID case, it's possible to find a distribution that makes EWA that does not work well. But so now I can regularize in the weights through time, thanks to a martingale argument and the quadratic variation term, additional quadratic variation term, in order to move from a regret bound to a cumulative risk bound in general with high probability. But I still have the open question that the quantile loss is not X concave. So at the very first, I don't have a regret bound for the quantile loss, and I know that. So I have to use another trick, which is the quantile loss. So the idea is instead of using, which is a gradient trick. So the gradient trick is the following one. Instead of using the quantile loss, I use the derivative of the quantile, which is just tau 1 minus tau, and then I linearize. So I use the difference between the prediction and my aggregation. And so that's another trick, which is called the gradient trick. And that then give you now new bound on the linearized regret, so that I call it regret tilde. And these bounds are now of this form, so they are bounds that depend on the algorithm itself. So that's bounds that depend on this quadratic variation term itself. So for the moment, if you look at that, it's a square root t bound in the worst case scenario. But so what is clear is that this, and that's why the gradient trick is used, is that this linearized regret is always controlling the usual regret. Okay, and so that's these kind of bounds are called second order regret bounds, and they have been proved for ML prod, which is another category by Pierre and Gilles Stoltz and Tim van Erben. All right. So now we have a bound that is a square root of t bound, but so we didn't use the yet the online to batch or the online to stochastic conversion, because of course this is a square root of t bound, because the losses, the quantile loss is not regular at all. So we know that we have to face a square root of t bound. But as now we can go to the with high probability to a stochastic environment and obtain the same bound for the cumulative risk, and this bound is true for without any assumption on yt xt. Now maybe we can use the regularity of our quantile risk, so the prediction, the expectation of the quantile, to obtain a faster one. And actually, that's what we show in full generality. So here it's just a kind of x-concavity, but on the conditional quantiles, on the conditional expectation of the quantile losses. And of course, the big restriction here is that alpha does not depend on t. So the nature can choose the conditional distribution as she wants, but she cannot. We need a kind of fixed regularity here. So in the sense that it does not mean that the conditional expectation or the conditional distribution has to be the same. It just means that we need a kind of regularity through time. And then we obtain, so we can move from this bound here to this one quite simply. So we obtain that the actually, so with high probability, I speed up the EWA and I obtain a robust bound. Okay, so this condition is called the Bernstein condition because it's not exactly the x-concavity on the conditional expectation, because here the conditional expectation is outside the square, but it's still satisfied in for the quantile loss in many cases and for many distributions. Okay, so now this is obtained if I know in advance the constant alpha here. But of course, alpha depends on the conditional distribution, so I don't know it. And I have to adapt to this alpha. So then I have to use different tricks. And one of them is really important in this kind of algorithm is that if you want to implement this algorithm, so we use the gradient trick, but then it's very difficult to control the magnitude of the gradients. And most of this algorithm so requires that the jumps of the gradients has to be bounded in some way. And this is not true in practice. So the gradients, the gradient steps, so the steps in your exponential may be very badly, and so numerically it's really a pain in the neck to implement these exponential strategies. So the idea is to use self-normalization on this. So the tilde version here is gradient losses, and so the idea is to multiply it by a certain learning rate that depend on the expert. So the J is the expert where we looked at the gradient, the corresponding gradient. So this strategy is called the multiple learning rate and was introduced by, again, Pierre Gaillard et al. In 2014. And then this idea stabilizes a lot the numerical implementation in the exponential weights. The problem is that the only requirement we had, so it was first to be bounded, but now hopefully if we manage to self-normalize nicely the gradient of each expert, we can hopefully be bounded. But the other requirement was that we produce a martingale. And now we don't have anymore a martingale because simply we multiply by eta j. So we depend on the index j. So we have actually to change the weights and multiply them by eta j. So now the weights are not anymore exponential weights. They change, they differ a little bit in the sense that we have the exponential of something that has been done to be more or less, let's say, as much as possible self-normalized. Time eta j. So actually eta j begins to be the crucial step here because in the exponential everything has been done to be stable. So this eta j is really important. And this eta j, we fit it we learn it, so the learning rates, we learn it thanks to strategy that was used for unique learning rate in Cesar Bianchi, Manchu, and Stolz. And so the algorithm is like this one. So you start with a cumulative loss at 0, you start with learning rate at 0, and then the weights, you put uniform weights on all your experts. I have M experts. And then at each time round, I compute the cumulative losses. So then I add to these losses, I add the second order terms that correspond to my correlation variation. Then I have to estimate the range of the gradients, because I said each gradient for each expert can be very badly, because some experts can be very, very bad. So I have to estimate the range of that. How do I do that? I do that by a doubling trick again. So in the sense that I only update the range, not when I. So the idea is to find to make that eta j is always smaller than the range, so that you self-normalize. So the idea is to find the largest possible observed, actually it should be a tip here, so the largest possible gradient losses that's observed before, and then you take the double of that. So you take, you have a safe strategy so that you do not change this bound at every step, and you stabilize a little bit the procedure. And then you look at eta j of this form here. So it's a kind of self-normalization for each different experts. And finally, the weights are computed in this way, so they are not completely recursive. So because the eta jt here is different than, so the eta j in front of the cumulative loss is a bit different than the eta j, because now eta j depends on t, so it's a bit more complicated again. So there are a lot of tricks to implement that rigorously and in a stabilized way, numerically stable way. Okay. So now some application. So of course the application is the one from Pierre talk. So the idea is that you have electricity consumption and you have 3 experts. So all the 3 experts are very good, and they are done to estimate or to predict the electricity consumption. So now I didn't want to produce good experts, because I wanted to show you the difference between the aggregations, and not if you can. But so assume that you want to produce many quantile predictions from these 3 experts. So of course you can add many experts and then do aggregation, or you can trust your aggregation procedure and just add 1 expert that is a lower bound to any possible forecast, and so this one is you cannot see it, but it's an upper bound of any possible forecast. And I'm interested in high quantile prediction, so I want to extrapolate. So the actual prediction made by the 3 good predictors here by mixing with this very poor constant prediction. Okay, but so trusting on the weights. Okay, so now is the implementation, and again, it's a very complicated problem because you use quantile loss on bad experts. But then you can see that exponential weights fail miserably. So in the sense that it's really, you can see that so I didn't produce the weights, but you can see that the weight fluctuates a lot, so that at some point it made 6 completely wrong, and then when they saw that so that's the interval of prediction produced by the exponential weights on these 5 experts, and you can see that so they are really too bad to be competitive. So why that again? It's because basically at some point in the weights they actually I understand it like that, but maybe it's not completely true. But at some point, as I told you, the exponential weights are doing good to minimize the losses. But the losses, the quantile losses, are minimized by experts that predict well the mean, the next observation. And so you can see that at some point, it's as if they change strategies and they start producing estimation of the next value, whereas they should keep on estimating the lower bound of the interval, for example. Okay. So, and then if you look at BOA intervals, they are, I mean, much more reasonable, so they are much more stable, and also, I guess they fit well. So the only information except the 5 experts here, the only information they need is actually so the tau, which is 0.05 and 0.95 in the loss. And then like that you can predict, thanks to 5 experts, as many probabilistic forecasts as you want by simply moving tau in a safe way. So actually, you have to be sure to be in the convex combination of
But here your initialization is at 0? So your online approach starts at time 0, or you got some prior...
No, online approach at time 0, so it's 0 here. So if you see at the beginning, you are very close to the mean, because
that's why it's not clear what's happening here.
The 3 experts are close to the actual prediction, and the 2 others are more or less at the same distance compared. So if you do the mean, you are if you I can show you.
So it's very fast because over a few points.
I can show you. That's exponential weights. Yeah, here it's okay. So that's Opera package with the output. So thanks to Pierre, we have nice plots, and it's very nice. It works very well. I'm advertising it. So that's the one for BOA. Okay, so here basically this expert is the upper bound. So it has to disappear in some way, or maybe not, I don't know, but it has to disappear because now we are focusing on the lower bound. So that's the expert. And so you can see that here, actually, yes, of course, more weights has been put it in the expert that unbiased from below in this case. Another thing is that here you can see the average loss suffered by the expert. So I'm warning you, and I warn Pierre, but he does not want to change. But so average loss has no meaning if you think of quantile losses. Because, so as you can see, a GBM forecast is doing very well in average loss because it's close to, it's a good predictor. So it's close to the next prediction. But here, what I'm interested in predicting in a stochastic environment that change, okay, through time. I'm interested in predicting a lower bound. So it's really something that it's a difficult problem in terms of stochastic because you have a stochastic environment that can be anything. So the prediction can, the conditional distribution can change. And so there is no reason that the average, the averaging from the classical average or the classical strong law of large number apply here on the quantile losses. So the GBM forecast does very well for the quantile loss, but it does not do well for actually predicting what we want, a lower bound on the lower bound on the or a lower quantile. Okay. That's the EWA, and if you think of EWA, here you see the weights that they are fluctuating far too much. So in the sense that so at some point they change their objective, so they move from at that point they move very close to the actual prediction and not the prediction of the quantile or the conditional quantile, and so then they change again the objective, and so that's the fluctuation here, for instance, of the upper bound that is responsible of this very poor interval of predictions. So okay. So to sum up, so as Pierre tell that the prediction interval are really important, or probabilistic forecast is really important, and it can be done thanks to the quantile loss in a nice way. But of course, we have to think about the meaning of the quantile loss in some settings. So it's really important to consider the stochastic setting in this case, so that we have some meaning on this quantile loss. And what we gain also is some regularity on the quantile risk with respect to the quantile loss. So then there exist algorithms that as BOA that are robust and adaptive in this case. And so as Pierre tells us, is that if all your experts are quite good, then of course the aggregation does not make a big difference. So for instance, for the square loss, as it's X concave, EWA is really close to BOA, and you cannot see the difference. But now if you change the objective and you want to start to predict high quantiles, so then it makes a difference, because first, it's not so simple to find good experts, and second, you can the problem is more difficult, and so then you see that the fluctuation of the algorithm itself can pollute the accuracy of the prediction. So it works well in practice thanks to the package Opera. It has been implemented at IDF, at Météo France, and at Vestis. So Météo France, they are doing a calibration, but I don't know anything about it. I will. There will be a conference where they will talk about it. There was some kind of they didn't want to. I don't know if they will publish something about it, but that's some privacy concern about. And Advestis is a company that it was a startup in finance and compliance prediction and scores. That is not anymore. That is too big to be a startup. Okay. So one perspective here is that, as I told you, what is a bit restrictive in that setting is that we used statistical learners, let's say, as experts. But actually, we would like to build them in some way, in some nice way. And one nice recursive algorithm that is quite general and works quite well in many, let's say, generalized linear models is Kalman filters. So really, Kalman filters are a good candidate to be experts, and so that we can aggregate Kalman filters with different state equations. So in a kind of dynamical state equation. Another example of aggregation used on statistical learners was, and what was the first example, it was Metagrad by Cullen and Van Herven. So they didn't use BOA, but another algorithm that is very close called Squint, which is almost the same. And so they aggregate online gradient descent algorithm with different learning rates. And the idea is that each of these statistical learners had some different behavior, and then we want to compete. So yeah, but I don't know how it works in practice, because maybe, to my opinion, OGD with different learning rates are still very close one to the other. So I don't know if the aggregation boosts a lot these methods. I think it's better to find algorithms that are more different. But here the idea was to adapt, that OGD can adapt the learning rate to the curvature of the curve of the loss function online.
It's actually invented at CWI. That's like it's an Amsterdam production.
Oh yeah, exactly. Yeah. Actually, all the I should have mentioned Peter Grunwald, but all the stuff I present is after a discussion with Peter Grunwald on the use of quantile losses in online setting. We had some discussion about understanding what was going on there. And he did a lot of work to, and actually he is also, I think, the main author in this Bernstein condition, Cullen, Van Herven, and Grunwald. And he's an expert on this kind of regularized loss by taking into account distributions and stochastics. So maybe I have some time, and I would like to show you another application. We were talking about how to use experts, how to use aggregation to produce or to adapt then experts. So one work in that respect, but it was a very specific work with Pierre Gaillard. It was to find spats rates in IID settings. So it's the most simple stochastic setting, so it's much more restrictive than before. And the starting point was to try to get, so forget about the red part here now, and when we compete with one expert, we obtained a bound with high probability of the form C log m plus x. Now, as you said, it's maybe sometimes you want to compete with
What's the Fluent?
Yep.
Fluent what you want.
Okay. But so you said that you want sometimes to compete with something else than convex combinations. And so when you introduce something else, like now you want to compete with pi star, which is in Rm, then of course you cannot obtain bounds in C log m. You have to take into account sparsity. So the sparsity means how many coordinates this optimal, this minimizer that are non-null. In the sense that if there is a minimizer or a parameter close to the minimum that is very sparse, so that the non-null coordinates are very few, then you can boost the prediction, and then in the IIT setting, you know how to boost in a nice way. It's a lasso algorithm. The lasso algorithm makes that in a very nice way by simply using the penalizing the empirical loss by L1 penalization on the set of parameters. Okay, so then again, if you have a one sparse solution, then you are back to the problem of expert setting. Okay, so it's quite natural to try to adapt the expert setting to that case, because there are very few online algorithms with nice and optimal guarantees, and so aggregation algorithm in expert advice setting are one of the few of them. Now we know that they have a very, very nice and very broad cumulative risk and with a fast rate in a high probability bound. So it's the best that you can do. So starting from algorithm as BOA, the idea is to try to adapt it to learn the parameter space in order to get a bound like this one. So it was the idea of Jertinovic in 2013 that actually proved that it's not so simple like that, because if you start by discretizing Rm and then looking at each point in Rm as an expert in the grid, then you have a problem of complexity. So you need to find something else. And so we had an idea of a strategy, so it's quite theoretical yet, but the idea is to learn from the aggregation. Okay, so the first crucial step, but I will be very short in the first crucial step was to look at what kind of nice guarantee has lasso. Lasso has a nice guarantee because they have an intermediate step in the proof somewhere of to obtain the fast bounds. They have a step like as lasso is minimizing the square loss plus an L1 penalty, then it has this rate of convergence that is a slow rate of convergence, but with a constant here, okay, that becomes small if pi j, this one is sparse. So now, what we get by using the second order regret bound of BOA and its stochastic version, we get something quite similar in the sense that we obtain second order bound like this one, so a slow rate of convergence with a kind of total variation distance here between the weights of an expert that is itself a linear so an expert in this case is a linear combination of the explanatory variables, and so and the minimizer. Okay, so starting from that, we then had in mind that maybe if now we can play here something that is getting closer and closer to the minimizer, then we can boost from a square root of t bound to a 1 over t bound. Okay, if this start to be as 1 over square root of t, then we achieve a fast rate of convergence. And we have to do that in a way that we keep track of the sparsity. Because we can be close to this one, but if pi j is 0, and then we decrease at 1 over square root of n, then we still sum upon all the variables, and so we are suboptimal. Okay. So we obtain an algorithm which is like this one. So here again, what is important, maybe I've been a bit fast. So you have experts that are linear predictors, and so you put these experts in BOA, and that's one set of experts. You could take as many as you want, and then you add corners of the L1 ball. So because you want to extrapolate. So in our case, we optimize only the L1 ball, and to extrapolate, we take the corners. So the corners will always be there, and to explore the L1 ball, we need now to know where to explore. So which kind of expert we have to add from that corners. And so the idea is the following one, is to use a doubling trick again. So we use sessions that are longer and longer. And at each session, what we use, we start with only the corners. And then they compete all together, and BOA give weights to all of them. And then what we will produce a linear predictor from the weights of BOA themselves. So we say, okay, if this corner had a lot of mass thanks to BOA, certainly I have to add an expert that is close to this corner. So I will add several experts there, close to this corner. So how I add these experts? I use averaging of the weights on the whole session, on the weights of BOA. So on average, which is the corner that had the most weight. And then I do sparse version of it. Because the problem with exponential weights is that they are never equal to 0. So they are always exponential minus something. So you need really to truncate them in some way. And so that's what we did. And so then you add them. And so you have several experts in the corner again. You have weights. And then you run again BOA on this new setting with new experts. That gives you new weights. And again, you average these weights we assign to the different experts. And an average of linear expert is still a linear expert. And you add all these linear experts, etc., etc. So the great advantage of that strategy is that, compared with the grid, is that it's not exponential, and you control nicely how many experts you
It's increasing, isn't it?
No, because you forget. So
I mean, because
you only keep track of the corners. You only need to keep track of the corners. You keep track of the corners, and then you at each point you.
So some of your which got closest you threw away then.
Yeah. Yeah.
But you're keeping always the corners.
Yeah, always the corners. They are they are essential to extrapolate. Okay. And then you obtain these guarantees, so they are not as good as the one from Lasso, because you can pay in some difficult cases where the optimal is on the edge of the L1 ball. You pay the sparsity to square. So maybe I can just show you this picture to finish. So if of course you are inside the L1 ball, then it's very simple to find a convex combination. So you remember that you always have the, just put one side of the one board here. That should be like this one. So by keeping the corner, of course, by convex combination, I have also the complete edge. And then it's very simple to aggregate with a theta prime here, to aggregate and to find something close to theta, which is the minimizer. But now, if theta itself is on the edge, then it's much more difficult because, I mean, at each step, you cannot use the information from theta prime, because even if theta prime is close, the convex combination of the corner plus theta prime that is the closest to theta only use the corner. Okay, so that's why here we needed to project theta prime on the edge in order to have the sparse version of theta prime, in order to be able to compete with these cases where you are close to the edges. Okay? So that's a case where, but of course it's more a theoretical setting where you can use feedback from the weighted algorithm in order to produce experts. Actually, we needed to use doubling trick, so to stop the algorithm at some horizon and then to restart it. An open question is whether you can do that online. That would be very nice. I mean, to learn simple experts from weights, I mean, online, so each time, but maybe you can overfit, or at some point it's difficult because you always want to also extrapolate, so you don't want to be that the experts are too precise themselves, because then you cannot extrapolate. So I don't know, it's still an open question. So we have a new rate of convergence here, so we don't know if it's optimal or not, because we have the sparsity up to the square, but the setting is a bit broader than the one of the lasso. And finally, we just play in the one ball. It was very important because it's simple to extrapolate in the one ball. You just take the corners. But how can you do that in a convex optimization problem if you don't know the size of the one ball at first? Then you have to adapt. The idea is to adapt, so to run several algorithms, and again to use experts on the size of the one ball. So it's not so clear what you will obtain. So thank you for your attention.
But there you're restricted to linear experts, right?
Yeah. So that's.
But you can always use kernel tricks or.
Yes.
With fixed function, you can always change the basis. But we do not learn the kernel.
So I have a question about the loss function. So you use the pinball, the quantile loss.
Not yet, not for the last.
No, I'm talking about the first.
The
first presentation.
Yeah.
The pinball loss. So and you have advantages when your loss behaves nicely, if it's concave and all that. So did you try the asymmetrically squared, so the expectile?
No. We didn't try. That's a good point. Yes, I mean it's really interesting, and so you have a lot of work in scoring to find the best score, and so the nice point with the quantile. So as I told you, the gradients are the gradient trick is nice, but it's a pain in the neck to bound because you have in the gradient trick you have a linear here you have a linear term, and then it becomes a square. So if one expert here is far away from the optimum, then you start to be very big, and numerically it's bad. But the nice point with the quantile loss is that this part is only tau or 1 minus tau. So this part is quite nice. If you start playing with this one, then I guess it may be. So it may be that EWA works better with exponential weights, and BOA works. But I didn't try.
Well, I also have a question to the quantifier part. You assumed at the very beginning here also a convexity of your weights. Could you relax this assumption at the beginning?
The convexity of the loss, or
Of the weights, of the pies. So you
Oh.
had all the pies were positive and
Yeah.
some equal to 1.
yeah. Well, I'm not in favor of that, but maybe we can try. But so there is a constant need for that. But exponential weights, everything here is based on the fact that exponential weights comes from the Kullback-Leibler divergence for on the simplex, on distributions, and so that's why we have the exponential everywhere, and that's optimal. I would say that if you start thinking of extending that to another space, you should think of the natural norm in this space, which will not be the Kullback-Leibler divergence because it's not defined for. And then to look at the let's say the primal problem, and so I would say that exponential then the exponential in the use of the exponential is really related to the simplex for deep reason, but as I told you, you can adapt with experts at the end of the to get something on the L1 ball. I mean, you basically here, okay, if you want to translate from the simplex to the L1 ball, then here, instead of xj here, you take fj of x. So you're expert x, and then you obtain a new strategy that competes in the L1 ball with exponential weights. Okay, but I would say that in order to do that in the L1 ball, so we have some assumptions like this one that are very restrictive compared with the assumptions that we have on the simplex. So you lose a little bit the idea that you can take any statistical procedure, even statistical procedures that are really related. So let's say OGD with two different gradients but the same OGD algorithm, non-linear algorithm. Then in this case, this kind of assumption will never be satisfied because it's only done for let's say orthonormal design or close to orthonormal design. So you really need to have good design to optimize in something else than the simplex. Because yes, when you can see if you start playing with minus and plus, you can add negative weight somewhere and add more weight somewhere else, and you don't change so you have a badly posed illness post problem. So it's much more difficult to get that. But it, of course, it's a very interesting and very natural. Yeah, it's a very difficult.
So, last question. Suppose you want to estimate all the quantiles at the same time.
Yeah.
And you consider a matrix of weights.
Yeah.
Is it an obvious extension, or is it harder, like if you try to do it at the same time to get the entire distribution?
Yeah. So from the perspective of weights, it's an easy extension in the sense that you can use different tau. But as Yannick tell you that you still have to to be sure that you order well your quantile predictions, and so that makes something that is not. You are not sure that it will be respected by your algorithm, even if your algorithm has nice theoretical bounds. It can be completely stupid in terms of if you want to predict two quantiles that are with levels that are quite close one to another. It may be that at some point there is a cross in the quantile that is completely stupid because you know by yourself. So this information should be included in the loss. And that's a very difficult problem from scoring rules. And I think there is a dilemma in this respect, in the sense that Nighting and co-authors show that you cannot do the best for each quantile and be coherent in the same way. You have to find a balance.
But that's why there was this paper in Econometrica where they was just saying, I mean, if it's let's say random and not so often, you just swap the
Okay, yeah.
no, but
okay,
and they
that's
showed in
interesting.
terms of empirical loss that it's the best you can do. Just accept it. And
Okay.
if it's sufficiently rare and random, it's not for specific conditions. Then the swapping is going to. I can find again the.
Yeah, please, yeah.
It's
Certainly, it's not the same community at all because I know people who work hard on the scoring to find a clever, smart score. But what you say is much more simple and if it works.
But you could constrain your weight.
And
right?
people do that in practice.
And you can constrain your weight, yes.
If you have this matrix and each row are the weights for each quantile, do you have an obvious constraint on this matrix so that it guarantees that all your quantiles will not
Yeah,
cross?
because if you have linear.
Because it's a linear combination, I think you can.
Maybe,
Yeah, you could actually explicitly.
If you order the price.
Anyways,
Maybe the last one before that.
I was just wondering whether any of these ideas have been explored in a multivariate setting. If you wanted to really learn a multivariate Y and wanted to find a weight matrix in that context, where you really want to also update
Yeah.
the dependence, right?
Yeah, then it starts to be much more complicated in the. I have again. I think the main problem is about, to my opinion, the main problem is about the score. So in the expert setting, if you have the good score, then you can do good things. But scores for multivariate quantiles, I think they are not so simple. But I just know one small part of the literature in this domain. So, but if you have the good score, I would say that it will work nicely, and so I think what is most important is that it's a good score. It's all the work of making a good score in a proper score. So in the sense that it's good for the expectation of the loss, and not on the loss itself. Because when you start looking at quantile, there is no point to look at the loss.
Okay, let's go eating.
Yeah.
And see you at 2 o'clock for the next one.
Thank you. The guy is called Chernozukov at MIT. And
Ah,
after
yes,
Gavichon, you know Gavichon, so il a fait un économiste en 2010. Et c'est à propos de ça,